So the cell communication disorder I chose was epilepsy. And before I can describe how it qualifies as cell communication, first we must go over what cell communication is. So cell communication is the process by which a cell detects and responds to signals in its environment. A ligand is very important in this process. It transmits signals between the cells by bonding to receptors. So different receptors are specific for different molecules. Insulin receptors bind to insulin, nerve growth receptors bind to nerve growth, and so on. So once a receptor receives the signal, it undergoes a change, and this results in biochemical reactions within the cell. And as we know, there's local and long distance. Local cells are touching very near to each other. Long distance, the signal must travel over a greater distance, and that's in the endocrine system, is an example of that. The signal pathway, so 3 stages of the transduction pathway. Reception, the protein at the cell surface detects the chemical signal. Transduction, change in the protein stimulates other changes. And response, the cell activity is activated. So, I'm going to start, well, no, not yet. Okay, so cell communication, how it can go wrong, and this mostly applies to epilepsy, especially with the neurotransmitters. So damaged neurons, this might change how they work normally or affect how they send signals. Too many or not enough neurotransmitters affects the neuron communication and can cause seizures. Some neurons have ion channels which are slower than normal, and this causes the message to not turn off as quickly as normal. And finally, neurons have many different synaptic receptors that receive the neurotransmitter. So this can make it harder for the neuron to stop or switch off the message, causing it to still send it after it is no longer needed. So before we get into epilepsy, I have a demonstration. So here we're just going to say that this is the presynaptic receptor and this is the postsynaptic. So this water will be the sodium ions, and they're going to send out an electrical signal, and it's going to fill up to about right here, and then it's going to turn off. The chloride ions are going to come in, and that's going to stop, and that way the signal can be performed. Now, in epilepsy, here the signal needs to be transferred from the presynaptic to the postsynaptic. The sodium ions are going to come in, and there's not going to be anything to stop them, so it just overflows. Now, if I was doing this randomly, you'd probably be like, oh my goodness, Bailey, what are you doing? Start freaking out. And that's what happens in the brain. There's nothing to cut it off, so it just starts sending electrical impulses, and now there's a mess that I'm going to have to clean up later. So, what is epilepsy? So this is the 4th most common neurological disorder, and it's defined as recurring seizures. It happens due to mutations in voltage-gated ion channels. These can be the calcium ion channels, sodium ion channels, potassium. There's several when it deals with this disorder. And the channel requires the neurotransmitter acetylcholine to open the channel. This is permeable to the sodium ions, calcium ions, and potassium ions. So depolarization, which is when the cell undergoes a shift in electrical distribution, occurs and activates these voltage-gated ion channels. And this creates the action potential. So a mutation in the sodium channel causes a slower inactivation to occur. The neuron is overly excited with ions, causing rapid firing of electrical impulses, resulting in convulsions. So sudden recurrent episodes of sensory disturbance, loss of consciousness, convulsions results in the disorder epilepsy. So, epilepsy at a closer look. These, like I said, the voltage-gated sodium ions are responsible for the depolarization, and they belong to a superfamily of voltage-gated channels, which are composed of protein subunits, and these are ion-selective pores. And the sodium channel comprises a single alpha subunit protein, which contains the pore-forming region and voltage center. It is associated with one or more accessory beta subunit proteins that modify the alpha subunit, but those are not essential. So, in a normal brain, neural interactions occur when an individual moves, feels emotions, maintains homeostasis, thinks, and the information to do these things is transmitted among action potentials. And this is between the presynaptic neuron, postsynaptic, like the water bottle and the cup that I had. And this process is called neurotransmission. So the brain cells normally communicate with each other by sending electrical and chemical signals across these synapses that connect the cells. But in people who have seizures, the brain's usual electrical activity is altered, and many of these nerve cells send at the same time. So the gene mutation responsible for epilepsy. So this gene is the GRBA1 gene, and it provides instructions for making one piece, the alpha-1 subunit, of the GABA receptor, and that is the gamma aminobutyric acid receptor protein. So the GABA receptor is a major inhibitor neurotransmitter in the central nervous system. Upon activation, this receptor selectively conducts the chloride through the pores. So sodium ions rush in, causing a rapid change, and this will send the chloride ions in to stop that. So the GABA system is a type of inhibitory transmitter in the brain which effectively stops messages from continuing to be sent. So it helps chloride ions pass into the neurons to send messages. So its main responsibility is to stop or switch off the message. So due to the mutation in the GRBA1 gene, it leads to the formation of an abnormal alpha-1 subunit that reduces the GABA receptor. And because this receptor contains the abnormal subunit, it does not reach the synapse, so the sodium ions are left continually going through, and there's nothing to cut them off due to that mutation. So I have this diagram. I don't know why it's blurry, but here you can see the sodium. Oh goodness. Okay, you can see the sodium coming in and the calcium, and they're going to go into this, the postsynaptic neuron, and this is the chloride coming in. So these are going to come through the postsynaptic to send out that electrical signal, and right here, this is where the chloride comes in, but due to that mutation, this is not going to happen. So all of these are going to come in, and there's going to be a shift in that electrical charge because, as you know, chloride is a negative, this is positive. So that's going to cause an imbalance, and that's when the brain starts sending those electrical impulses. So, because of rapid firings of electrical signals from the miscommunication between neurons, epilepsy does result in seizures. And these seizures can be grand mal seizures. This is a seizure that people typically think of whenever they think of a seizure. The person will fall, become unconscious. They have lots of muscle contractions. And these seizures can also be called generalized. They take place in the entire brain. The other one is the petit mal seizures, and these can also be called focal, and they occur in one point of the brain, and this can lead to blank staring, loss of consciousness. And that's just a picture I have of symptoms. So epilepsy is not inherited. Genetic disorders, environmental factors, missing or mutated chromosomes can affect it, but your risk actually increases to just 2 to 5% if your parents have epilepsy. Now, meningitis, tuberculosis can play a role in epilepsy since those do attack the central nervous system. But if your parent has epilepsy due to, let's say, a car accident or a tumor, their child is not necessarily going to get epilepsy. But chromosomes, as we know, are very important structures within the cell. And so this actually shows the ring 20 chromosome. I have it on my board over there. And it's almost never inherited. And so the formation of these actually affects normal development of the brain. So when treating this, they actually do an electroencephalogram. And this will show, this is just a painless test that will show what type of epilepsy you may have. And these are ways to treat it: the anti-electric drugs, vagus nerve stimulator, brain surgery. Actually, here on my diagram I have a hysterectomy where they will remove half the brain in children that are real young that have dangers with epilepsy. And let's see, life expectancy is you can lose about 2 years of your life with idiopathic and symptogenic, and symptomatic is a reduction in 10 years. But epilepsy, you can still live a normal life.